Okay. Good evening to everyone. So today we are going to discuss the last topic for this first CA. Okay. So I think we covered nearly 95% of the syllabus in the lecture videos. The last 5%. Okay. So the last topic is partitions and equivalence classes. Okay. Here, first of all, first I will explain this example. Once you understand this example, next you will understand this definition. Okay. So here, Z, that is the set of all integers. Now I am going to define 4 set. So these 4 sets are subset of Z. So how they are defining A1? A1 is set of all x in Z, set of all integers. Okay, but x is what? It's a positive integer. So that means A1 contains elements from where? 1, 2, 3, 4, and so on. Okay, next A2, set of all x belongs to capital Z such that x is strictly less than minus 100. So that means A2 contains the elements what? Minus 101, minus starting from minus 101, and then minus 102, minus 103, like this is going. Okay, because it is minus, that's why it is going like this. Okay, next is okay, now A1 and A2. So now what is the remaining elements? Okay, in Z. Suppose if I remove A1 and A2 from Z, what is the remaining elements we have? So the remaining elements is from minus 100 to 0. So that one I am going to divide into 2 parts. One is A3 is equal to set of all x in Z, set of all x in okay. So I think I explained A1 and A2. So A3 I told what? This remaining still we have what? Minus 100 to 0. So that one I am going to divide into 2 parts. How? So those elements from minus 100 to 0 which are divisible by 2. Okay, wow. So that is in A3. Okay, next those elements from minus 100 to 0, those elements, okay, that element should be minus 100 to 0, but it is not divisible by what? 2. That is in A4. Now, you can see these subsets A1, A2, A3, A4 are mutually disjoint. Okay, and they are union. If you take the union, you will get Z. Here Z is missing. Okay, the union is the whole Z. So in other words, Z equal to A1 union A2 union A3 union A4 and AA intersection AJ, mutually disjoint I told. So AA intersection AJ is equal to what? Empty for every I not equal to J. Okay, so and the I and J are belongs to where? This 1, 2, 3, 4. Okay, we say that P equal to the set A1, A2, A3, A4 is a partition. Okay, a partition of the set capital Z. Okay, so now this is a motivation for the definition partition. Okay, now here X be a non-empty set. Okay, maybe I need to. Yes. So X be a non-empty set. In the example, what we saw that instead of X, we saw that set of all integers. I'll put a column like this. Okay, in the example, this is an example, this is in the definition. So in the definition, we are taking in general X. Okay. Now, a collection P of non-empty subsets is said to be partition of X if, what is the first condition? A belongs to that partition implies what? That A is not equal to what? Empty. Okay, not equal to empty. Okay, so this is the definition. Okay, I think in the previous case also we see that like this only. You can check it. So if you take P, okay, P is what? A1, A2, A3, A4. I will take A1 or A2, A3 or A4. So this is actually what? Non-empty. Okay, each one is non-empty. Okay. Next, second condition. Second condition is A comma B. Okay, so instead of A comma B in P and A not equal to B implies what? A intersection B equal to empty. So this is comes from mutually disjoint. The last class, last page I explained mutually disjoint. So here A1 intersection A2 is what? Empty. So similarly, they will take two different elements from the partition, then its intersection is what? Empty. Okay, and then third one. Third one is X is equal to union of A. That A is from where? In P. So that is the last step. You can Z equal to what? A1 union, A2 union, A3 union, A4. Here you have only 4 elements. That's why we written directly. So in general, I don't know how many elements in the partition P. So that's why union A, those elements A, I will take from where? P. So a collection P of non-empty subset is said to be a partition of X if it satisfies these three conditions. Okay, now the members of capital P are said to be blocks of the partition. So that means what? In the previous example, A1 is a block, A2 is a block, A3, A4 are blocks of the partitions. Okay. Now in this section, we are going to show that equivalence relation on a okay. So actually, what is here these three lines? So if I give a equivalence relation, we can find a partition. Similarly, if I give you a partition, we can find a equivalence relation both way. So again, I'll repeat. Okay, suppose X is a given set. If I give you a equivalence relation, we can find a partition. Similarly, if I give you a partition, you can find a equivalence relation. Okay. Next definition, equivalence classes. Let R be an equivalence relation defined on a non-empty set capital X. So A is an element of capital X. Define a subset R of A of capital X by R of A is equal to set of all X in capital X such that this A and the element X, okay, should be what? Should be related. Okay, so I will write again. Okay, R of A. First, you should understand this definition clearly because I will use regularly this definition. R of A equal to set of all X in X such that A comma X Please wait a minute. Okay. So now R of A is equal to set of all x and x such that A comma x is an element of R. Okay. So now suppose uh, you have B comma x. Okay. B comma x is an R. Then you can write from the definition. Okay. Suppose B comma x is in R, then you can write x is in where? X is in R of B. Okay, x is in R of B. Similarly, if x is in R of B, you can write what? B comma x is in what? R. Okay, suppose A comma B in R. Okay, so then the second element, that means what? B belongs to R of A. R of A. Suppose B comma A belongs to R, then you can write the second element A belongs to what? R of B. Similarly, if suppose A belongs to R of B means you can write what? B comma A belongs to what? R. So in this way also you can. First you should understand this definition. Okay, now okay. So this is the definition R of A. This actually R of A is a subset of the given set. Okay. So that is called equivalence class of R determined by the element A. So this equivalence class R of A is also denoted by this symbol. Equivalence class of A, okay, suffix R. Okay, next. Properties of equivalence classes. Let R be an equivalence relation on a non-empty set capital X, then R of A is not equal to empty. Okay, for all A belongs to capital X. So why R of A is not equal to empty? The reason is this is an equivalence relation and hence it is what? Reflexive. So if it is reflexive now, then A comma A belongs to R. For all A belongs to A. You know that. Okay, so A comma A, it is reflexive means you can write what? A comma A is in what? R. So if it is A comma A is in R, implies the second element. What is the second element? A. First element is also A, but from this definition I am telling you. Okay, second element is A, is an element of what? R of the first element. Okay. So that's why A is an element of R of A. So this implies R of A is what? Non-empty. At least you have one element. Okay. So next, this is the first property. Next one is B belongs to R of A implies A belongs to R of B. Okay. So B belongs to R of A. Implies A belongs to R of B. I need to prove. Okay. So first I'll start from B belongs to R of A. Okay, B belongs to R of A. So this is a proof. B belongs to R of A implies, so A comma B is an element of what? R by definition. So this implies, we know that R is an equivalence relation. R is an R is an equivalence relation. So R is symmetry. Okay, yeah. This implies B comma A is in where? R. So B comma A in R na second element. What is the second element? A is belongs to R of B. R of B. That means equivalence class of B. So that is I assumed B belongs to R of A. I proved A belongs to R of B. It's over. Second property is over. Next, third property. What is third property? B belongs to R of A. Okay, wow. So implies R of B equal to R of A. Okay, just I will explain here. If you have any doubts, you can ask me. Then, if you have a doubt, then I will go to the board. So, okay, I'll take x a comma b in X first in general. Okay, and then you need to assume this also. B belongs to what? R of A. Okay, well, B belongs to R of A. I assume B belongs to R of A. So what I need to prove? To prove R of A equal to R of B, or R of B equal to R of A. Okay. So now proof. So here B belongs to R of A implies A comma B in R. A comma B in R. Okay. So this is the first step. A comma B in R. A comma B in R na, then B comma A is in also R because by symmetry. B comma A is in also in R. Okay. Next, I'll take an element, some arbitrary element, C in what? The left hand side. So let us take C is an element of what? R of B. So again, C belongs to R of B means what? B comma C in R. B comma C in R means implies C comma B is also in R. I think so. Okay, wait a minute. C belongs to R of B means B comma C in R. Okay, wow, B comma C in R. Okay. And then using these two. Okay, A comma B in R and B comma C in R. R is an equivalence relation. Okay, and R is transitive. So and hence A comma C in where? R. A comma C in R. Okay, my aim is to prove finally C in where? In the right hand side. R of A. Okay, wow. So if C in R of A means A comma C should be what? In R. Okay, wow. So next step, directly you can write A comma C in R implies. So what is the conclusion? Second element is second element is in where? R of A. So that's all. This implies R of B is a subset of R of A because I'll take an element from R of B, C, the same element in R of A. But what is our assumption here? B, when under this assumption only you proved this. Okay, that means if B belongs to R of A implies R of B is a subset of what? R of A. Similarly, next to prove if B belongs to R of A, that means again should assume this one. B belongs to R of A. Okay, I need to prove what? The other way. The other way means R of A is a subset of R of B. Okay, I'll take an element again. Okay, I think that is not explained here. They will put it similarly, you can write like this. Okay, now I'll tell you how to do it. Let C again I'll take the same element, or you can take a different element, C in R of A. So, okay, now, so before this, you can write this. Already you know that what B belongs to, sorry, B belongs to R of A. B belongs to R of A implies what? A comma B in R, and B comma A is also in R because of symmetry. Now I'll take an element C in the C in R of A. So this implies A comma C in R. So finally I need to prove what? I need to prove C in R of B. C in what? R of B. So this implies what? B comma C should be in where? R. Okay. Now, okay, B comma A in R, A comma C in R. By transitive, directly you can write what? B comma C in R. You can write directly from these two. So B comma C in R means C belongs to what? R of B.
అసలు మీతో ఇద్దరే ఉన్నారు, నేను ఇంకొకడు ఎందుకులే.
Now we are three. Okay, next one is so I think I proved property number 3. Property number 4. Property number 4 is if A comma B in capital X, then either R of A intersection R of B equal to empty, or R of A equal to what? R of B. So actually here, so it is enough to show that if I am assuming R of A intersection R of B, this is small b, is not equal to empty. If it is not equal to empty, means I need to prove what? R of A equal to R of B. So I assume that R of A intersection R of B is what? Not equal to empty. If it is not equal to empty, means at least one element is common. So I will take that element is C. So C in where? R of A as well as C in what? R of B. So C in R of A implies from the previous property 3. If B belongs to R of A, now you can write what? R of B is same as what? R of A. So similarly, if C belongs to R of A, then you can write what? R of C equal to what? R of A. So, okay. Next, already I told that this is not equal to empty, so they have a common element. So I took C belongs to R of A. Similarly, C, the same element C in what? R of B. So okay, C belongs to R of B. Again, I am using property number 3. Okay, property number 3. So property number 3 again. B belongs to R of A implies what? R of B equal to R of A. So using this property, R of C equal to what? R of B. Now combine these two. R of C equal to R of A and R of C equal to R of B. Left hand side is same, then the right hand side is same. So R of A equal to what? R of B. So that is I want to prove. Because either this is true or this is true. I am assuming the first one is not true. So then automatically I need to prove what? The second one is true. So I proved. Okay, that's all. So the next theorem is actually this theorem says that if we give equivalence relation, we can find a partition. Okay, that is the content of this theorem statement. So every equivalence relation R on a non-empty set capital X determines a unique partition on X whose blocks are equivalence classes of R. Okay, So the proof is a little bit short. You can easily write. Let R be an equivalence relation on a non-empty set X. From this, I should tell there is a partition corresponding to this relation. Okay. Let capital P be the collection of all equivalence classes of R. So that is capital P equal to set of all R of A. That is the equivalence classes of A such that A is an element of what? Capital X. So then we note that each element of P. So what is the element of P? R of A. Okay, well, suppose A in X na R of A is the element of what? P. B is an element of capital X na R of B is an element of capital B. So each element of capital P is a non-empty set of X. That is property number 1. We proved R of A is what? Non-empty. Because A belongs to what? R of A. Second one, if R of A is not equal to R of B, then by the last property. What is the last property? Either this is true or this is true. But in the proof, I assumed what? This is not true. That's why I proved what? This is true. Similarly, you can assume what? This is not true. Then you can prove this is also true. So that's why they are telling that here. If R of A is not equal to R of B, then property of equivalent, which property? Last property, property number 4. Okay, we have what? R of A intersection R of B should be what? Empty. Okay, and then last one. If X in capital X, then X should be in one of the equivalence classes, that is X in what? R of X. So if you take any element, okay, any element from capital X, that element should be in one of the equivalence classes. So you can write the given set X is equal to union of all what? R of A. So in the example, this is Z union what? A1 union A2 union A3 union A4. Like this, X is equal to union of R of A. A belongs to capital X. Okay, now if you okay, these three statements only I am going to write slightly in different way. Okay, you can check it now. Thus, every element of capital P is a non-empty subset of capital X. So here what? Each element of P is what? More or less here each element of capital P is what? Non-empty subset of X. Here they are writing what? Every element of capital P is what? Non-empty subset of X. Here it is not that much difference. Here it is in the notation. So if these two are not equal, then its intersection is what? Empty. So they are writing in words. How they are writing in words? Any two distinct elements of capital P are disjoint. So any two distinct elements are what? Disjoint. That's all. And then third one. X is a union of members of P. Okay, check it. X is a union of members of what? P. Okay, members of here P is a partition. Here R of A, each one of them is a blocks of the partition. Okay, so P is a partition. Why it is a partition? Because just in the beginning of the class, I gave the definition of a partition. So X is a non-empty set. A collection P of a non-empty set is a partition if it satisfies these three conditions. And what is the condition? If A belongs to P, A is not equal to empty. So that is the first condition we saw that. And then any two distinct element is what? Whose intersection is what? Empty. And X is equal to union of A belongs to P. So And then you can see these three conditions are satisfied here. Yes. Okay. Condition 1, condition 2, condition 3. So by definition of a partition, P is here partition of capital X. As each block of this partition is of the form R of A for not same, sum A belongs to capital X, comma, each block of P is an equivalence class of R. Okay, this partition whose blocks are equivalence class of R is unique. Why it is unique? As R equivalence class of any element is unique. That's why uh, this partition is also unique. So next, the unique partition capital P as X determined by an equivalence relation on X is denoted by X slash R. Okay, it is also called X modulo R. So X modulo R is set of all equivalence classes of X, which is determined by the relation R, such that X is in capital X. So this is a theorem without proof. So what it says, so if I give you a set and if I give you a partition, then you can find a equivalence relation. So the previous theorem says what? If I give you a set and if I give you a equivalence relation, you can find a partition. But here just opposite in theorem 8. Now we'll go to the problem. So A is 1, 2, 3, 4 and P equal to partition 1. This is first equivalence class. This is a second class 2, 4 and then third one. Find the equivalence relation R on A determined by the partition P. So you can easily find, look at here, this contains only what? 1. So you can write in the equivalence relations first 1, 1, 1, 1, 1 and then 2, 4 in the other class. Or you can say these are the two blocks. Okay, okay, each one of them are blocks. Blocks are the partition. 2, 4 is in the equivalence class, means you can write 2, 2 and then 2, 4 and then 4, 2 and then 4, 4 and finally 3. So you can write 3, 3. So that's all. This is a equivalence relation from this partition. Similarly, next problem, A is a given set which contains 6 elements. P is this partition. Partition is given. They are asking the equivalence relation. So how to find the equivalence relation? 1, 5 means 1, 1, 1, 5, 5, 1, 5, 5. Next 2, 3, 6 means 2, 2, 2, 3, 2, 6. Next 3, 2, 3, 3, 3, 6. Next 6, 2, 6, 3, 6, 6. And then 4 means 4, 4. Suppose if I give you a partition, okay, find the, sorry, here they gave the equivalence relation. They are asking the partition. So here look at 1, 1, 1, 3. Okay, suppose R of 1. R of 1 means equivalence classes of 1. So 1 is related to what? 1. So that's why I'll put 1 here. 1 is related to 3, 3. 1 is related to 5, 5. Okay. So, and hence R of 1 is same as R of 3 and which is same as what? R of 5. Here this is not R of 2. This should be what? R of 3. Okay. Now R of 1 is same as R of 3 is same as R of 5. So remaining you have 2 and 4. If I take 2, 2 is related to 2 and 2 is related to what? 4. So and hence R of 2 is same as what? R of 5. So totally 5 elements. So these 3 are same. Okay, well, these 2 are same. That's all over. So now the partition of P is now what? 1, 3, 5 and 2, 4. Okay, here they gave the diagram. From this they are asking what is the partition. Okay, you can easily tell 1, 2, 4 is a partition, 3 and 6 is a partition, 5 is a partition. The next problem is the first part is you need to prove R is an equivalence relation or not. The second subdivision, they are asking the partition. So let capital X is equal to 1, 2, 3 up to 100, capital X, and R is the relation. Okay, set of all x comma y such that x minus y is divisible by 7. 7 is not visible here. X minus y is divisible by 7. Determine whether R is an equivalence relation or not. If it is an equivalence relation, determine the partition X which is determined by R. So that is the meaning of X slash R. So already we discussed so many problems in equivalence relation. Okay, so this is also a similar problem. So okay, first we need to prove reflexive. Reflexive means what? X is related to X. So here, when we say that X is related to X, X minus X is what? Divisible by 7. So okay, X minus X is equal to what? 0. You can write 0 equal to what? 0 into 7. So and hence X minus X is what? Divisible by 7. So X is related to R. So and hence R is reflexive. Next is symmetry. So symmetry means what? If X is related to Y, that implies what? X minus Y is what? Divisible by 7. X minus Y is divisible by 7. Now you can write X minus Y is equal to what? 7 into M. So Y minus X is equal to 7 into minus M. Okay, or you can write minus 7 into M. Okay, better to write 7 into minus M because it is divisible by what? 7. Okay, wow. So 7 into minus M is correct. So Y minus X is divisible by what? 7. So Y minus X is divisible by 7. Na? Y comma X is in what? R. So whenever X comma Y in R, this implies Y comma X is in also R. That's why it is what? Symmetric. The last one, X comma Y in R and Y comma Z in R. So X comma Y in R means X minus Y is divisible by what? 7. And Y minus Z is divisible by 7. Then if I add these two, X minus Y plus Y minus Z equal to 7 times M plus K. So again it is a multiple of 7. Or you can write Y gets cancelled means X minus Z equal to what? 7 times M plus K. So X minus Z equal to 7 times M plus K is not visible. This is M 7 times M plus K. So this implies X minus Z, again the typo. This is X minus Z is divisible by 7. So thus, whenever you have X comma Y in R and Y comma X is in R, implies X comma Z is also in R. So it is what? Transitive, and hence R is an R is an equivalence relation. Okay. The second question is, if it is an equivalence relation, determine the partition what? X determined by R. So what is the equivalence classes here? If I take, because you have what? 1 to 100. So I'll take 1. So 1, 8, because it should be divisible by what? 7. And then 15. Similarly, you can write. Okay, so then equivalence class of 1 is same as equivalence class of 8, equivalence class of 8 is same as equivalence class of 15, and so on. The next to 2, 9, 16, 23. Okay, similarly for equivalence class of 3. Okay, so you should write box. The left side of box is not visible here. So you should write these are the equivalence classes. So other than this, you cannot find anything because if you take the union, you'll get 1 to 100. You can check it. So suppose equivalence class of 7 means 7, 14, 21, 28, 35, 42, and so on. So the partition P is equal to the set X, okay, determined by R is what? Equivalence class of 1, equivalence class of 2, up to what? Equivalence class of 7. Now I think this PDF is over. There is one more PDF. Okay, so here already we discussed the first and last actually in this proof. So here if R is an equivalence relation on a non-empty set capital X, and if A and B are element of capital A or arbitrary, then A belongs to, this is equivalence class of A. So already I proved R of A is non-empty. Okay, well, R of A is non-empty because A belongs to what? R of A. The same thing here they done it. So R is reflexive. A comma A belongs to R. For every A belongs to R, then the second element. Okay, this is the second element. Is the belongs to R of the first element. R of A, or you can write what? Equivalence class of the first element. Okay. So that is a proof for the first one. Second one, uh, equivalence class of A equal to equivalence class of B if and only if A comma B in R. So how to prove this one? Okay, I will write here. Just I'll give the outline. Equivalence class of A equal to equivalence class of B if and if and only if A comma B in R. Okay, so now I think first I prove the easiest part, and then I'll go to the next part. Okay, so now okay, I'll take let us take equivalence class of A equal to equivalence class of B. We'll take like this. So that is explained in the last three lines. So we know that A belongs to equivalence class of A. Similarly, you can say what? B belongs to what? Equivalence class of B by what? Subdivision number 1. But we know that equivalence class of B is same as what? Equivalence class of A. So this implies B is an element of equivalence class of A. If B is an element of equivalence class of A now, then you can write A comma B in what? R. Because by definition. Because we know that A comma B in R now, the second element is an element of what? R of the first element. Or you can write equivalence class of first element. If B belongs to equivalence class of A now, you can write what? A comma B are related in R. So I assumed this one. Okay, this one I proved this one. The first part is known. Second part, I'm going to assume this one. I'm going to assume what? Assume A comma B in what? R. To prove equivalence class of A is same as equivalence class of B. Okay, so for this, okay, A comma B in R na, then A is related to B. Okay, so this implies sorry. Okay, first they will take X in equivalence class of B, or you can take equivalence class of A also. Okay, so this implies X in B na, B comma X is in where? R. Or you can write B comma X is in R. Now A comma B in R and B comma X is in R. Now A comma X is in R. I think so. Okay. So sorry. Okay, you can see here from 1 and 2, a comma b in R, and then b comma x is in R, na a comma x is in R. So using these two and using R is transitive, we can write, since you should write like this, since a comma b in R and b comma x is in R and R is transitive, comma we have what we have, a comma x is in R. A comma x is in R. Okay. Actually, what I need to prove, I took an element from the right hand side. Finally, I'll prove what x should be in where? The left hand side. Okay, wow. So you can check it. A comma x is in R na implies, can you say that the second element is what? X is in what? R of A. Or you can say what? Equals class of A. That's all. So this implies under this condition, okay, wow. If I take an element x in the right hand side, I'll prove the same element in the left hand side. This implies equivalence class of B is a subset of what? Equivalence class of A. First part is over. Similarly, again I should assume what? This one. Okay, well, this is a common assumption for both part. Okay, now I need to prove equivalence class of A is a subset of what? Equivalence class of B. Okay, now I'll take an element. Here I'll take x, that's why they'll take what? Y. Y in what? Equals class of A. So this implies A comma Y is an element of what? R. Okay, now already A comma B in R. Okay, wow. So finally, suppose nothing is striking means what is the last step? So you should think about like this. Last step should be what? Y in what? Equivalence class of B. So what is the previous step? You should think like this. So B comma Y. Okay, wow. B comma Y should be in R. So how I can get B comma Y in R? So next you should think. Okay, wow. B comma Y in R. So look at this one. This is a common assumption. I told that. So this implies, okay, wow, this implies A comma B in R implies B comma A is also in R by symmetry. Now using this and using this, no, not this one. And this is correct. I think instead of this one. Okay, using this and using this. So B comma A in R and A comma Y in R, and using R is transitive, B comma Y in R. Okay, now I got this one. Once you got B comma Y in R, you can write what? Y belongs to equivalence class of B. Hence, you can write what you can write. Equivalence class of A is a subset because I took Y in equivalence class of A. I proved the same element in the equivalence class of B. That's why equivalence class of A is same as equivalence class of B. So now combining these two, okay, combining these two, you can say that equivalence class of A is same as equivalence class of B under the assumption what? This assumption. A comma B in what? R. You should assume this one for both parts. Okay, to prove this one also I am assumed this one. To prove this one also I assumed this one. Okay. Next, last one already we discussed. Okay, so what is the last one? If equivalence class of A interaction equivalence class of B is not equal to empty, they are not equal to empty means what? They have a common element, then they should be equal. They should be equal. So how it is true? Okay, you can see here. So okay, wait a minute. Hello. Thank you, Vasandan. Okay, I think I explained something. The thing is, what I explained here is, okay, its intersection is not equal to empty. Okay, intersection is not equal to empty. Then they are equal. Okay, so I gave an example. What is the example means? So here you can see here, equivalence class of 2 equal to equivalence class of 4. Okay, because they have a common element. Okay, so okay, so either they are equal or the intersection is what? Non-empty. Suppose the intersection is non-empty, they should be equal. I'll go to the proof. Okay. Okay. Now the third one. Okay. What is the third one? Third one is if equivalence class of A intersection equivalence class of B is not equal to empty, then I need to prove equivalence class of A is equal to equivalence class of B. Okay. So I assumed equivalence class of A intersection equivalence class of B is non-empty. If it is non-empty, then they have a common element. I'll take the common element X, which is in both equivalence class of A and as well as equivalence classes of B. So if X is in A, equivalence classes of A, then you can write X is related to A. Similarly, X belongs to equivalence classes of B implies what? X is related to B. But by symmetry, you can write A is related to what? X. So A related to X and X related to B. By using transitive, A is related to what? B. If A is related to B by property 2, what is property 2? Where when A is related to B, then you can say what? Equivalence class of A is same as what? Equivalence class of B. Okay, well, so using that property, okay, when our A is related to B, we have what? Equivalence class of A equal to what? Equivalence class of B. So that is, we want to show that. If it is not equal to empty, we need to prove equivalence class of A is same as equivalence class of B. So next, within 5 minutes, I will finish it. Partial ordering. Okay, already we discussed enough problem in partial ordering, but just I'll tell some more examples and then we will close the class. Show that the relation greater than or equal to. Okay, show that the relation you can see here. The greater than or equal to, we see a partial ordering on the set of all integers. So partial ordering means I need to prove 3 conditions: reflexive, antisymmetric, and transitive. So we know that A greater than or equal to A for every integer A. So that's why A is reflexive. Sorry, the greater than or equal to is reflexive. Okay. If it is greater than means you can't say A greater than A. It is not true. But it is A greater than or equal to A. Okay, it's true for every integers because here what is our set on the set of integers. So that's why greater than or equal to is what? Reflexive. Okay, next for antisymmetric, you need to assume what? A is related to B, A is related to B, and B is related to A. So you need to prove A equal to B. A related to B implies what? A greater than or equal to B. B related to A means B greater than or equal to A. So A greater than or equal to B and B greater than or equal to A implies A equal to B. Okay, that we know that. So the relation greater than or equal to is what? Antisymmetric. Transitive, it automatically come. A greater than or equal to B. That means what? A related to B and B related to what? C. Implies A greater than or equal to what? C. So transitive. So it's a reflexive, antisymmetric, transitive. So greater than or equal to is what? Partial ordering the set of integers. Therefore, the set of all integers with respect to greater than or equal to is a partial ordered set or POSIT. So next, so show that the divisibility relation. This is not L, divisible. Okay, or slash. Okay, divisible is a partial ordering. On what? On set of all positive integers. So Z plus is a set of all positive integers. So first we know that A divides A for any positive integers. So that's why they don't take integers, because in the integers you have 0. You can't say 0 divides 0. So that's why they will take carefully Z plus. Okay, so A divides A for any positive integers. So that's why the relation is what? Reflexive. Next, A related to B, that means what? A divides B, and B related to A, that implies what? B divides A. So then automatically we know that what? A equal to B. So and hence the divisibility relation is antisymmetric. Third one, A related to B. So that means what? A divides B. B related to C implies what? B divides C. Okay, so A divides B and B divides C means automatically A divides C. Okay, so and hence this is a transitive. Finally, it is what? uh, Finally, it is partial ordering or poset. Okay, and the next problem, show that the inclusion relation, we call this is a set inclusion. Okay, a set inclusion. How the notation is? This is what? Set inclusion. Okay, properly I write. This is set inclusion. So partial ordering on the power set of the set is. So S is a given set. For that set, you should find a power set. Okay. Okay. Now, what is the set you have? Power set of S and set inclusion. So now I am going to show that this set inclusion is a partial ordering on power set of S. Okay. So we know that A is a subset of A. Okay. For any subset. Okay. Whenever A is a subset of A. So and hence it is what? Reflexive. And then symmetric. A is a subset of B and B is a subset of A implies what? A equal to B. So this relation is what? Antisymmetric. And third one, transitive. So A related to B is what? A is a subset of B. B related to C implies what? B is a subset of C, implies A is a subset of C, and hence A is related to C. So therefore the relation is what? Transitive, and hence this is what? Partial ordering on P of S means power set of S. So next one is provide an example of partial ordering on, where what is your set here? R is what? Set of all real numbers. So here the example is, you can take less than or equal to also you can take, or greater than or equal to also you can take. Okay, so it is actually less than or equal to is what? Partial ordering on set of all real numbers. Similarly, greater than or equal to is also a partial ordering on what? Set of all real numbers. Okay, and then example 3.50 is a particular case of example 3.48, because here they will take any set S. For any set S, they are finding the power set. But here, instead of S, they gave some particular set A equal to ABC. Okay, show that the relation against a set inclusion is a partial ordering on the power set of a set A, where A is what? A comma B comma C. It contains 3 elements, means power set of A contains 2 power 3, 8 elements. That means all the subsets of A, here it is listed out, empty set, singleton set A, singleton set B, singleton set C, and then the whole set ABC. Similarly, you can write okay, all the subsets of A. Now you can easily say that okay, this set inclusion is what? Reflexive, antisymmetric, and what? Transitive. So this is automatically come from example 3.48. Okay, next one, and maybe this is the last one. Yes, this is the last one. Describe whether the relation divide and the integral multiple or partial ordering, because we know that the relation divides. A divides A, so and hence reflexive. Whenever A divides A and B divides A, okay, again I'll repeat for symmetry, sorry, antisymmetry. Whenever A divides B and I think power is okay. for antisymmetry, whenever A divides B and B divides A, you can say what? A equal to B. And then for transitive, A divides B and B divides C, then you can say what? A divides C. So next, integral multiple. Okay, wow. So you can say A divides B means B is an integral multiple of A. Okay. So that is the meaning. Okay. When A divides B means what? B is what? Integral multiple of what? A. So again, B is this divides is what? Partial ordering means. Similarly, integral multiple is also what? Partial ordering, because any element A, because A divides A implies what? A is a integral multiple of A. Similarly, A is a multiple. A is a integral multiple of A. So A is a multiple integral of B, and B is a multiple integral of A implies A equal to B. Okay. Similarly, last one, A is integral multiple of B, and B is integral multiple of C. Then you can say A is integral multiple of C. Okay. So that's why divide and integral multiple are partial ordering. So this is syllabus for up to the first CA. The hash diagram is not included in the first CA syllabus. That's why I'll stop here. Thank you for your patience and listening my lecture. Okay, thank you, Vasandan. Okay, let me revise the topic: open statements in logic. So, in particularly, can you tell which example with one or two examples, open statement? So, in my notes, if you tell, okay, any example is okay. So, just I want to know open statement. I think the open statement, I don't know exactly what you expect. Okay, I will show the PPT. You can tell which wow, open statement. Actually, in the open statement, this is the only one slide. Actually, you can see here. Okay, so and then it starts from quantifiers, and then for all x, for every x, it goes like this. So the problem is start from I think next theory of inference for predicate calculus. Okay, so these are the problems. So my suggestion is uh, please read my notes or your class notes. Okay, so even though if you don't understand, okay, which part you don't understand, okay, that one you can take a snapshot and then send to me. I will try to explain through message, or otherwise I will call you. We will discuss over phone. Okay, Vasandan? Okay, thank you. Okay, welcome. Thank you.